Okay, so we are going to come back to a machine learning perspective with the talk of Claire Monteleoni, who is a director de recherche at INRIA and also professor at University of Boulder, with another perspective from the climatology point of view. Thank you very much.
Thanks so much. So here's a photo I took a couple years back in Colorado, in Aspen. And I like it because it's kind of aspirational, that somehow we've got nature, wildlife, and even human infrastructure coexisting. So we have some wildlife using this bridge, we've got power lines, but somehow it's a big happy family. This is maybe what we can strive for. And then here's a not so happy picture from Colorado. And I give this as an example of the large impact that extreme weather events can have on societies, and especially when they combine together. And so the anomalous condition here was drought, and in this region, our moisture comes from snow, which we usually receive in the fall and winter. And as of New Year's Eve, there had been no snow that year, so that was extremely anomalous, and the ground cover was very dry. The other thing that was anomalous was how strong the winds were when a snowstorm did come in. So about a day before we actually got snow, we had these extremely high winds. Sorry, I forgot to change to kilometers. And all it took was an ignition, and we basically got a storm of fire that moved very, very quickly. It jumped over the major highways in the region in multiple places, carried by burning embers. And it leveled some of these suburban communities. So these are the traces of houses that were lost that afternoon. We lost over 1,000 homes. It's not a wildfire in that it was not in the wildlands. This was in suburban Denver, so between Boulder and Denver, there's suburban areas. And it wasn't even a forest fire in that it was carried mainly just by low grasses, not even trees. So these are not people living at the border of wilderness. These are some suburban neighborhoods. And this is just one example of extreme events. It's something that we can see today, and we're increasingly seeing, for example, in the Mediterranean region, a lot of these wildfires and floods, and et cetera. And then also, given the research coming from GIEC or the IPCC, there's the climate change that we don't necessarily see as immediately. But given these extreme events and their impacts and the warming climate that has been shown, I've been trying to direct my AI and machine learning research towards these problems, towards addressing climate change for actually nearly 20 years. And this is really now quite a widespread effort. We have these big events like these, and at Davos, the World Economic Forum put a call to action in a white paper in 2018 saying, yes, AI can help us find cats in images, and it can improve our GDP by speeding up industry, but can we take the benefits of AI back towards protecting our Earth? And we're starting to really have critical mass in this domain. I actually just flew back from Rio, where we wrapped our 14th conference on climate informatics. We've actually been in business 15 years, but 1 year we did only an online hackathon due to COVID. And we've found that making these events that are standalone events is really important for building a community. So events such as these are really important. Make sure to socialize at the coffee breaks and the lunches. This is where those individual connections and collaborations are made. One thing we've found really useful are hackathons. We saw that cited earlier, because we bring together, even at the student level, people with all different expertise. And for interdisciplinary research, it really comes down to those relationships. And to students in the room, I would say, you have some competence or interest that brought you to this meeting. If you're more on the AI side, walk across campus and work with someone working on climate change. If you're more on the climate side, There's several AI people in the room, like my team, fifth row from the back, and some deep minders. So make those collaborations. And the collaborations doesn't have to be with a senior famous person. Actually, if you're a student and you find a peer, a student to work with, go rock climbing with, whatever it is, that's how you build those collaborations. And I also just want to say that we've had climate informatics in the US. We launched it in New York, held it in Boulder, Colorado for many years, in Paris at ENS in 2019 before the pandemic, and then at Oxford and Cambridge and the Turing Institute. And this was our first year in the Global South. The attendance was a lot lower due to visa challenges and funding issues, but I'm really glad that we did start making inroads in the Global South. But I would also just make a quick plug. We wrapped less than a week ago, so we are now very open to people that want to volunteer to maybe host next year. So it's kind of like this, but for several days long, and there's a hackathon, a lot of students, and et cetera. So please let me know if you're interested in that. So at INRIA, we have just launched a team called ARCHES, which stands for AI Research for Climate Change and Environmental Sustainability, where we work on a range of topics. And I'll, in this slide, give you a taste of the topics, although I'm mostly going to focus more on methods today. And I've arranged these in terms of time frames. Some folks at IPSL have kind of pushed back on using these time frames, but okay, so some of these time frames are not mutually exclusive. But when we talk about, say, those wildfires, we would like to have, AI-driven warning systems that do a better job of warning communities in the directions of possible spread. And here we're talking about climate change adaptation. Whether or not we can prove that the increased incidence is directly caused by climate change, these are events that we're already facing, and especially in the Mediterranean region, we would like to have better tools to warn communities. And this is also where we interface with society, and I'm really concerned with maintaining or actually increasing climate justice. At least in the US, we've seen a legacy of climate injustice where communities with less resources are often targeted for incinerators or other polluting entities, making them more vulnerable to climate change. So for example, with wildfire, we want our AI warning systems to warn communities in the likely path, as well as communities that may be farther afield but are more vulnerable, say, to lung disease or degraded air quality due to a legacy of climate injustice. Mitigation is what in French is generally called atténuation, which is what actions can we take now or maybe out into the medium term, the next several years, to reduce the worst risks of warming, in some way reduce our carbon. And here we mostly try to accelerate the transition to renewable energy. We have projects with EDF here in France where they want to know, how are the wind circulation patterns changing, right? We have all these éoliennes, these wind turbines, but what if they're not in the optimal position for the new circulation? Because it's not just a general warming trend, we're actually seeing changed wind circulations. And in fact, there's starting to be some empirical evidence that average wind is decreasing. But what happens to this probability mass? Well, we get more mass in the tails of the distribution, meaning we might have really intense wind some places, but then we don't even have the right operating characteristics of the wind turbines to exploit that. So they'd like to get better predictions of these wind fields, and similar, they want to do that for the photovoltaics, is rethink it to make it future-proof. And then we can talk about long-term impacts, where governments are asking us these really hard questions to predict out, 30, 50, 100 years, and really often at a quite specific level, like, NASA has funded us to look at what is the sea level rise trend going to be, but specifically down to islands in the Pacific, very local predictions. So the kind of take-home message about our approach, so one, I'll mention our approach in terms of data, and then our approach in terms of methods, because I like to summarize things at the beginning of a talk. I think we were one of the first groups that took the approach that, hey, there's different kinds of data in this domain, but as an AI designer, why can't I make use of all these different kinds of data? And so in particular, the numerical weather prediction models and the general circulation models, which discretize the dynamics and the physics, as we've heard in some of the previous talks, we could actually treat those as sources of data because they create these simulations that are very high dimensional. They get us into the big data domain. They're on a nice geospatial grid. They're made by experts. Many of them are in the room who have been working on these problems for many, many years. So they actually encode a lot of domain knowledge and physics. And why else? Well, because in the future we have zero data. This is our only glimpse into the future. And it's actually true also with the distant past. So all of this wonderful observation and remote sensing data that we have is just the past, say, decades that we have that available. And as we go out into the past, we have some records and some paleological proxies that we can look at, tree rings and ice cores, but it's very, very sparse. So the physics-based models are the only view into the distant past and into the future. And then I'm lucky that I'm already going after some of the talks that have explained data assimilation or reanalysis data, but this is a really interesting sweet spot that has allowed for the revolution in AI for weather. I'm sure Mark's talk later will get a lot more into data assimilation, the process that generates this data. But as an AI researcher, why can't we use all these different types of data? And in terms of methods, these days we're leaning very heavily on methods that are unsupervised because just in general, for any problem, even if I'm just trying to learn cats in images, there's more images of cats than there are images of cats that have a box around the cat or have been labeled with a text label saying cat. So in general, there's more unlabeled data than labeled data. And also in our setting, we have all these different fields, and we don't necessarily have a label or a supervised task that's clear to us, but luckily there's been this revolution in self-supervised learning, which is an approach to unsupervised learning that I'll talk about. We also use generative AI. Now, this is a dangerous keyword. Gen AI is out in the news and generally refers to a large model trained on text and video that can be used to create fake videos or other things. We're going to take the same technology, the same models, and instead train them on data that we care about here, some of the fields that were shown for ClimSim, or in the case of EDF, the wind fields that we want to model. And so we're using generative approaches, and I'm also going to focus on them in this domain, but not with pre-trained huge language video models. I've long been interested in learning under non-stationarity. That's actually how I got into this field, and I'm not going to talk about it today, but I'll just use it as sort of an entree to say you're a core machine learning person and you just happen to stumble into this day, well, welcome. Please join this field, and you're going to be able to actually advance core machine learning and core AI also by working on this field. In fact, I'll point you to our new ICML position paper arguing that the innovation that really happens when we're designing ML for specific applications has a real value in advancing the field of machine learning research. Okay, but today I will talk more about techniques. So I'll talk about self-supervised learning and generative learning. And then I'll show some applications. I will get back to the revolution in AI for weather, as was introduced this morning, and that we'll hear more of in the afternoon. And then I'll make a quick plug on trying to take the benefits of AI to work towards climate data equity. Okay, so this slide is meant to be very simple. I've been in events where this is the first math that was seen on a slide. Luckily, that is not the case. Thank you very much for the previous speakers for having a lot of math on your slides so that this won't look overwhelming. This is meant to look very simple, to make a simple distinction between supervised learning and unsupervised learning, in particular for deep learning. So you've heard all these jargons about different architectures and et cetera. I'm going to throw the whole choice of architecture just under the hood and just represent my neural network by its parameters, capital W. And then my neural network acting on an input example will be f of W applied to an input example x. And then whatever the network outputs, I'll call y hat. Remember, x can be a vector, a matrix, a tensor, and same with y hat. But let's boil down the learning of deep learning to just how we're going to fit these parameters W. So we're given a lot of labeled data, so input examples x with their desired label, y, and then we design a loss function such that when we do gradient descent on the loss function, we're trying to drive the output of the network y hat closer to the desired output, which we call the label y. And then learning is just a kind of noisy, approximate version of gradient descent of the loss function that I've written down, where backpropagation talks about how you apply the chain rule for taking derivatives to get the individual parameters of the network W updated, because they're at all different layers. Okay, so if that made sense to you, then there's nothing scary about moving to unsupervised deep learning. Yes, it might be scary that we don't have a label y, but we can just now write down loss functions that don't depend on some external label for a data point x. So all I've done in the bottom is I've just called the output of my network x hat. Nothing else has changed, but I do have to change my loss function so it doesn't depend on some label y, because I don't have one. So you can certainly think of objectives for clustering that depend only on the input data. And then I'm going to talk about how to design objectives, other objectives that that only depend on, say, your input data or functions of your input data and the output of the network. But assuming you can do that, and we're going to talk about that, then learning is exactly the same. I'm just doing some noisy version of gradient descent on my loss, and then backprop is how I use the chain rule to walk through the network and give my incremental updates to every parameter in the network. Okay? So the approach to unsupervised learning that is most widely used and successful, and actually I think general, is called self-supervised. And if you've heard of contrastive learning, this falls into that approach. If you've heard of masking, well, that also falls into this approach. And so I need to define one piece of jargon. So machine learners are famous for their jargon, as are climate scientists. I've tried to underline and define jargon, but again, feel free to stop me for clarifications. So I need to design a pretext task. And what is that? So I have my data, and I don't have some external labels, but I can still use the data that I have to set up some kind of task that I will then train a model to do supervised learning on, meaning my labels basically have to come from my available data. This is vague, but we'll get to some examples. Then I'll train a model to do this task, so train it in kind of a supervised setting, given how I set up my pretext task. That's a pretext task. It's not useful, though, unless I've designed it in such a way that after doing this, the features that are learned in the weights of the network will somehow be useful for another downstream task. And as we get into the generative part of the talk, then I'll explain to you what I mean about the distribution that you learn. Okay? So most of you have actually already seen a pretext task, maybe without even knowing it. I think one of the simplest examples for those who have had an intro machine learning class is the autoencoder. So there's a lot of weights to be fit, forget the labels encoder, decoder, but there's weights to be fit and, architecture choices between that grayscale image and this other grayscale image, and those are what we're going to fit. But once this thing is trained, it's a useless machine. I mean, I give it an image, and it's practically the identity function, but actually worse. It's giving me something like more blurry than my input. So that's because this is just a pretext task. The goal is not to just have this machine. The goal is that after learning the machine, I've fed a lot of images from the same distribution through. I've tried to bring the output of the network close to the input of the network, and at the end I get this bottleneck layer, which is a lower dimensional weight layer that can serve as a compact representation of the data that I trained on. So the pretext for learning this machine was just a pretext for getting this dimensionality reduction. Okay, so you've probably seen that before. And so how do we apply self-supervised learning in climate and weather? I'm going to give an example, which is one large approach that we actually take, which is using AI and machine learning for downscaling. Downscaling can be done from climate data or climate model simulations, and it's taking data at a coarse grid and generating data at a finer grid. And the use case is very clear when we think about climate models, and there are use cases across our domain applications and objectives. But as we heard a little bit in some of the previous talks, when a modeling team gives predictions to the IPCC or JEC, they're running these global scale climate models. No surprise, they're not simulating snowflakes or the hail, the grêle that we saw over the weekend, but you might be surprised that there's a fair amount of moist processes and clouds that don't make it into the model. So one approach we've taken is to use machine learning to, you could think of it as super resolution, to take coarse scale data and bring it to fine scales. Say Météo France cares about where to put the wind turbines. If I just have one box of a climate model representing all France, then it's going to be hard to decide about different states or regions that I want to put this wind field. Okay. Why can't we just use existing AI methods? I mean, for some tasks we certainly can, but I claimed that you could still advance core AI by working in this area. So, we have data evolving with time. This seems suspiciously a lot like an image, because if I have a real value for temperature at every latitude, longitude pixel, then I've got an image with real values. And then I have time, so this is a tensor, or you could view it maybe as video. And that's actually what you'll find. If you'll look for algorithms for learning for spatiotemporal data, if you actually use that keyword, spatiotemporal data, you'll get papers with that title coming out of the top AI conferences for computer vision. The problem is they were developed with the end goal of analyzing video, either Hollywood video I capture on my cell phone. But basically, there's a notion of depth that we don't have when we're just looking at real valued geospatial fields. And even objects are very hard to define in our setting. I mean, they do talk about learning from deformable objects, like a cat deforms as it walks, but not as much as some convection that may occur and then may dissipate, basically these diffuse and ephemeral patterns on fluids. And in particular, since we don't have objects, we don't have edges. So We wanted to downscale data in time, meaning we had geospatial data evolving at time, but at some frame rate, maybe 6 hours, and we wanted it to be 3 hours. And so my student, Nidin Haralal, found in the computer vision the state of the art for this task, and we needed to do it in an unsupervised or self-supervised way. And it was based on optical flow. Optical flow is cool if you have video with a high frame rate because you're tracking pixels that have similar behavior across frames. And so you can pick up on objects or edges, but it has actually horrible non-physical artifacts when training the state-of-the-art at the time temporal interpolation algorithm from computer vision, which is based on optical flow, training it from scratch from two different geophysical tasks. This is a very fine resolution reanalysis data set called CARA over Greenland. And this is a coarse resolution climate model simulation from the IPSL. And with both of them, you see these terrible streaked artifacts. So Nidin came up with a new method called stint, which may even hallucinate some physics, but in general is smoother and seems a lot more physical on not just these kinds of data, but several other, so all the geospatial data sets that he tested it on, it outperformed the optical flow-based methods. And this was a really clean, nice idea of designing a pretext task. So we have the time series of images, and the images that we have in the training data are indicated by blue, and I'll just call the frame rate to be integers 0, 1, 2, etc., indexed by t. So what we want for downscaling in time, also known as temporal interpolation, is a machine F that takes the images at the two endpoints of a time interval and outputs an image that would be between those two endpoints, ideally. And if we had such a machine, then we should be able to then take these intermediate outputs at time 0.5 and 1.5 and do the same tasks. They differ by a time interval of 1. And so the image that we output would have been the AI's view of what the image at time t equals 1 would be. But I've circled that here because we actually have that image in the training data that we can compare to. So this is how we're going to compute our loss function, is that we have to be cycle consistent with respect to the data that we actually have. So it's an extremely simple idea, and it's also a setting where I have not made use of any exterior labels. These are intermediate outputs of my algorithm, and my algorithm is trained on the training data that I have. And I'm taking as a label something that's actually in my data. So this is the simplest version, just for you to get the gist. To kind of get the best performance and avoid trivial minimization of the objective, he played around and found that it's actually good to have multiple different cycle consistency checks in your loss function, even if they're between intermediate outputs of your algorithm itself. And then he also found that when we have a loss that has these different checks, we want to put the most weight on the checks that are back to the original data. So this does not perform on a standard vision benchmark. If it had, I would be presenting it at a vision conference. But it does outperform the state-of-the-art in vision on a variety, this is actually not all of them, different types of data, satellite data, reanalysis data, IPSL data at different time frames. The baseline was just to repeat previous images, but super slow-mo is the red curve, the thing to beat. Okay. So now I'm going to move on to generative learning, and just a quick note, from here on out, we're still kind of in the self-supervised category because many of the techniques we are training in a self-supervised way. But back to that simple autoencoder, often you're going to have a dense autoencoder. If you're trying to do dimensionality reduction, that means you go through a lower dimensional layer. But when you think about neuroscience or cognitive science, people are actually looking at wide autoencoders because apparently that's how living beings often encode observations as mapping to a higher dimensional space where there's sparsity and different observations can be held far apart. But anyway, so this is the autoencoder, and there's just a single latent representation, but what if I'd like to have a probability distribution over lower dimensional representations? Well, you've probably heard of the VAE, the variational autoencoder, and this was sort of the first approach to that because they're fitting a Gaussian, so you have some prior. You still try to pull the output of your network close to your input, but you're also fitting a good Gaussian for your data, and then you're often regularized by something that brings the Gaussian back to its prior so that you don't overfit. But if you want to get away from Gaussians, the next step was normalizing flows. And so here, you still start with your simple prior, but you have a series of invertible simple transformations to get potentially a quite non-Gaussian representation or posterior over your latent space Z, but the math works out nicely because these are all invertible, and the neural network is learning the parameters of each of these invertible functions, which we call the flow. So hold on to that. I'm going to show an example of using this for generative downscaling. But of course, we are also very interested in diffusion training. We'll talk about this in the weather section. And actually, this also falls into the idea of self-supervised training, because I have examples of the data that I want to generate, in this case, celebrity faces, but it could be the data cubes with wind, pressure, et cetera, that you have. And then I'm going to create some fake data from that, and I'm going to create these image pairs. So each pair is so the first pair is made by adding Gaussian noise to all the pixels randomly, a certain amount of noise to take sort of one step in this direction, and that's going to be my pair x0, x1. And then the next pair is made by adding noise to x1. So then I can do supervised learning, where I'm learning in the other direction. So I'm learning from, I'm learning from xt to xt minus 1, so that I can take a fully noised image, and with this model that I've learned, which is the probability of the less noised image given the more noised image, I can then generate samples that are similar to my original distribution. But again, I created this data set just from my training data set, and so again, this was now a self-supervised training. Once I've learned this function, p theta, that conditions on the image that I give it, then the inference, as I actually already mentioned, was I can sample a completely noisy image, so the pixels are IID from a Gaussian, and then I can just go back in this other direction, applying my learned p theta to sample my next xt minus 1, given xt. Okay. And these days, we've been looking more at flow matching. There's this whole field on stochastic interpolance, but this paper from ICLR 2023 by Lipman et al. Makes tweaks to the noise update so that you actually can get through this noise flow using fewer steps, because somehow it's like a straighter path. So we're going to talk about flow matching usually, but it's a diffusion style training that's much faster than previous diffusion trainings. Okay, applications of generative AI in climate and weather. This is a highly ARCHES focused related work, because mostly I'm going to talk about ClimaLine, which is generative downscaling in an unsupervised way, and then I'm going to talk about ARCHES Weather Gen, and ARCHES Climate. This does relate to GenCast, which we're going to hear about later from Remy. And I also want to point to a beautiful PhD thesis by Clément Brochet of France, who did probabilistic ensemble generation actually using a style GAN. And I skipped right over GANs, but that's also a form of generative learning. Okay. So Brian Gronke, who did a master's in our group and is now finishing up his PhD at Alfred Wegener in Potsdam, noticed that we could take normalizing flows and we could do downscaling. And this is the traditional downscaling in space, where before we did an example of downscaling in time for stint. And I said, from an AI perspective, I will just use any kind of data, and I mean, I should understand where it comes from, but usually you would think that you would downscale from a climate model simulation. As I said, you know, Jack is modeling France in one box, but I want to do it at the specific wind field. But actually, for this application, we used a reanalysis data set for our coarse resolution and actually a numerical weather model for our fine resolution. Okay. And we did separate trainings and experiments for temp and precipitation. Okay, so what he noticed was that we could use a domain alignment technique that was based on normalizing flows called align flow, and this was from Stefano Erman's group, Aditya Grover, in AAAI 2020, and treat this as a downscaling task. So now, instead of X being an example and Y being a label, they're just two letters, two random variables that we're going to assign to actually the same field, but at different spatial resolutions. And domain alignment is saying, I've got samples from the marginal of one of the variables, say X, and I'd like to be able to then, from that, approximate the marginal of Y. And then I would like to have this be invertible so that if I have samples from the marginal of Y, then I can use F inverse to approximate the marginal of PX. And the way this is done in align flow is to make a relatively standard assumption we make when we have complicated joint distributions, which is to assume there's some conditional independence. So we can say X and Y are conditionally independent given some Z, that's basically the latent distribution that we're trying to learn. Because if we make that assumption, then we can get a flow from X to Z by fitting a normalizing flow, a flow from Y to Z by fitting the normalizing flow, and then we have our prior that we assume on our latent space Z. And then we've approximated the joint, which means we can downscale, we can upscale, and those are the things we can do conditionally on a map. We could also just sample unconditionally from the joint and get images at both low and high resolution. And interestingly, compared to the previous literature that we're aware of on statistical climatology and statistical downscaling, this was the first step towards an unsupervised method, meaning we didn't need paired maps. I didn't need to know that on this particular date, this was coarse resolution precip, and this was the fine resolution precipitation at that same time and date. We just needed access to IID samples from of both of the maps. And then we do get something unsupervised in that there's we don't need our examples to be paired over time. It helps if there's some alignment on the spatial bounding box, right? The technique will work better. Here we're looking at part of the continental US in the southeast. It's generative. So to do downscaling, I would input a coarse resolution image, map it to the latent space, and then I can sample conditioned on that image, fine resolution images. And there's some level of interpretability, but I will say interpretability of generative models is a core AI, largely open problem. Like the positive results I know of are showing some tests to show that your GAN didn't memorize your training data. So anyway, it's a rich area for core machine learning research. But this is an interpretability through an interpolation. And I've skipped how the model is trained. You saw the math. But say that we already have the model trained, and I've got, and then I give it the upper right and upper left image, which are fine scale precipitation images. I can ask for a temporal interpolation between these. So I map this image through the flow that maps the latent space from fine scale images, and then and I can also sample conditionally to get a coarse scale image if I would like to somehow upscale these. But how do I make this walk? I've mapped this guy to its latent space and this to latent space. Well, there's actually an entire literature on how to walk through the latent space. So once you're kind of non-Gaussian, you're ideally walking this posterior, which is, you want to do a geodesic path, but the posterior might be quite complicated. And then you get into efficiency issues. But then we can use the kinds of techniques that we have from non-convex optimization type of things, where we make like a linear approximation, and if we go off the geodesic, we project back. So there's a lot of other people working on this. But say you have a way to connect 2 points in the latent space, then you can generate the fine resolution image and the coarse resolution conditionally from those points on the latent space, and then you can give it to a meteorologist and say, look, this is what the AI thinks is how this precipitation pattern evolved over time between these 2 points at fine and coarse resolution. Okay. So just a quick recap of where we are so far. So STINT is a pretext task for temporal downscaling of geospatial data. It's unsupervised, but it works best when the input data is spatially aligned. We're trying to get this published. A preprint is available. ClimAlign used normalizing flows, in particular the align flow algorithm, for just general downscaling, spatial downscaling of geospatial data. And STINT was general temporal downscaling of geospatial data. This was published in the Proceedings of Climate Informatics 2020. And Brian has shared some code on GitHub, so I linked that as well. And again, this is unsupervised in that it does not require temporal alignment of the coarse and fine scale data, but it does work best when the samples that you get are spatially aligned, at least at the bounding box. And kind of the key idea of self-supervised learning is that there's some underlying process or actual signal tying your observations together. Like when we saw those spatial fields from ClimSim, we didn't have to necessarily include all the input data fields, because these are simulations from climate models, and the climate models themselves have entangled those fields. And then even if you're not working with a climate model, these are all observations from an Earth system where the fields are entangled based on the underlying physics and interaction with the topography. So just a recap or outlook from those works is we're interested in pretext tasks that are that would allow us to simultaneously downscale in space and time. So I want to learn features in space and time, or in like a manifold I can get to from those. And the pretext task is general if the features that are learned are useful for other downstream tasks. Okay, climate and weather. So jumping into the neural GCM and GenCast realm, just a quick review. European funding and a lot of really smart scientists working on data assimilation got us this amazing data set called ERA5. And this is from the European Center's website. Basically, they're taking a lot of different observation types and getting like gap filling, getting them onto a spatial grid by applying conservation laws from physics, so conservation of heat, energy, etc., pushing the data through the physics to get a gridded data set. But this data set is so good that any tech company could come along with their favorite deep learning model, train it autoregressively to predict for the weather state, and they did pretty well. I mean, not any company, but like Google DeepMind did a really, really good job, and same with Huawei. It's autoregression saying, I want to predict my next state, where next could be 6 or to 24 hours ahead, and then it's rolled out. We had a nice slide from Michael on that, but the idea is that I've trained a model to predict forward in time 6 hours, or say 24 hours, so this model should be able to predict from the starting state to the state at day 1, and then take that weather state and feed it into the same model. You should be able to predict now day 2, and et cetera. And there's skill up to about 7 to 10 days ahead. So our team, namely Guillaume Quiron, who's here, and Renu Singh and others in our team, said, can we actually match these results using much less compute? Because we're actually funded by the French government. We have fewer GPUs than Google by many orders of magnitude, and the GPUs are being bought up by Meta and the other big competitors. How does an individual researcher get to play in this space? So one thing that Guillaume wanted to do was actually use a coarser version so that we had fewer data points to train on. So a lot of the AI for weather results were trained at 0.2 or 0.25 degree resolution in latitude, longitude. He trained at 1.5 degrees. He also looked at which models the code was available and were performing well, which is the one from Huawei, Pangu Weather, which was doing a similarly kind of self-supervised or masked architecture known as a Swin transformer. And they did have these 3D convolutions so that you could deal with the height in the atmosphere. But that's quite heavy computationally, so he slimmed it down to just doing 2D attention over lat lon, and sort of a smart way to couple that with the 1D attention over the atmospheric column. And so, not even talking about generative learning here yet, this is just results for the deterministic model. He did much better on the trade-off between training time in terms of GPU days on just a V100 and improvement in mean prediction score over a variety of variables. For example, this much improvement from neural GCM, and also improving over the European model. Okay, but we really want to go generative. Why is that? So when you have multiple ways that things can go, but you're being asked to optimize for average performance, you'll probably generate a prediction that is just the average, but is completely non-physical. So this storm might go one way or the other way, and to perform well on an average prediction, we should predict some fuzzy smudge that is actually not a physical way that the storm could go. So we wanted to do probabilistic ensemble generation, and then the goal is that each sampled member should be more physical. So we can compare this to neural GCM, and it seems like these are the physical comparisons, different fields of data. It seems like the dynamical core is only really needed for Z500, atmospheric pressure. And there are some things that neural GCM is actually not simulating, so we just compared to IFS and to our version that used diffusion-style training instead of flow matching. Okay, you ask, but what about the statistical measures? Well, first off, these are CRPS skill scores. But we did do a lot of different statistical measures, including the ensemble score, which is a multivariate version of the CRPS, and the spread skill ratio, which is supposed to be close to 1. So here it seems that neural GCM is over dispersive. Our vanilla diffusion style Arches Weather Gen is under dispersive, but IFS ensemble and Arches Weather is just right. So yeah, we saw the first row of this plot, and it's just kind of amazing that such a cheaper model is almost the same as GenCast and Neural GCM here. We didn't have the results from GenCast to put them in these plots, so we were really glad when Stephen Rasp implemented it into Weatherbench 2. And then these are variables that Neural GCM doesn't do, but were very comparable to GenCast here. So I would encourage you to look at the preprint. This is also in submission, and also at the more general GeoArches package that you can contribute to and download data loaders and et cetera, as well as the code for Arches Weather and Arches Weather Gen. And so how did we do this? So actually one idea that's a little bit similar to Neural GCM. Neural GCM predicts forward using the dynamical core and then uses the neural network to get a better prediction of the residual. Here we predict forward using Arches Weather, so our deterministic SWIN transformer that I mentioned, so an AI model. But we then only do the diffusion style or the flow matching training to predict the residual. So we'll predict forward one weather mean state, and then we will do an ensemble generation for better matching the residual beyond what the mean state can predict. This is where the flow matching update comes in. So if you're used to standard diffusion, this will look a little bit different. And actually, we're not just using one instance of Arches Weather to figure out the residual. To get more confidence on the residual, we'll take the average over several reinitialized runs of the deterministic model. So I'm coming up on time. These are some of the fields. Here's different seeds, so 4 different ensemble members for this water vapor variable that is very important. And they look pretty, they look similar, but we can just take a snapshot 10 days later and we actually are getting different physics as desired. We can look at the ensemble mean and the variance, a lot of things that many people in this room are better at looking at than us, but let's see what the reviewers say. But what are the remaining challenges? So I mentioned that we're usually training the deterministic models to do average performance, and that's not great for extreme events. And doing this generative training is one way to address it. But as Clément pointed out, Dauvilliers, it's actually often a limitation of the data, because ERA 5, for example, if we're thinking about tropical cyclones, doesn't include the max wind speeds observed in observations, because part of what happens when you push these things through physics is a fair bit of smoothing. And this is not great for extremes, and we know that the extremes are highly societally impactful, and also we could lose out on really important tipping points if we're smoothing too much. So we need to use multiple sources of data, including observations, and Clément has a new architecture for that, which is going to be in the proceedings of this climate informatics. I won't linger too much on the second bullet. This is the kind of stuff we talk with Mark about. So how do we do data assimilation in the AI setting? I did plug that evaluation of generative models is still largely open. So when somebody generates a bunch of fake clouds using a GAN, and then as a future work says, you know, evaluate to what extent this matches the true distribution, well, I mean, good luck. That's also open in core machine learning. But we could ask, how is this going to fare for longer timescales? I'll just go very quick here. So this is something Graham is working on, Graham Klein, and he gave some oral presentations last week at both EGU and Climate Informatics. And so he took Arches Weather Gen, he removed column-wise, because we're trying to predict out decades. We're not going to be able to model the vertical column. He included greenhouse gas forcings, and he learned an emulator of some IPSL simulations, where he's now trying to predict 1 month ahead in the training, and then he's actually rolling out for a decade and then multiple decades, and seems to be pretty good in terms of matching the data he trained on, and even without being told, recovering the climate change trend. So I did just want to take a moment to make a plug for using AI to improve climate equity, and in particular climate data equity is one place. And just a trigger warning for this picture from the US, where a meteorologist, Jack Sillen, just superimposed the statistics on Black Americans, so Black, Indigenous, and people of color percentages in the grayscale by these statistical areas, and then weather radar in the green circles. And just reading from the legend, many majority Black parts of the Southeast USA are relatively far from radar sites, meaning that it's harder to gather information, data, about storms impacting these areas. So if we don't even have weather data, it's hard to produce fair predictions. And this is an economic problem and a political problem, but if there's anything AI can do to help equalize this, I would highly recommend it, which is that we can train models when in places and times where we have more data, apply them in low data regions. If we do have some data, we can fine tune, or we can train models in low data regions to generate more data. This is true not just in local scales, but more globally, where the global north has been generating a lot of this anthropogenic carbon, and also we have more data, and the global south is typically suffering more of the effects. So thank you, and thanks to the team and the funders, and feel free to join the GeoArches package.
Thank you very much.